So the next thing we have to do is to interpolate, go back and forth between the grids. So let's go back to MATLAB, and we basically need two functions. One function is interpolating from the fine grid to the coarse grid. Let's call it restriction. So you restrict x to x coarse. All right. So to do that, you estimate the size of x again, and I basically want to say that my xc, okay, so my n coarse, let's say just n divided by 2. All right, my xc then is equal to zeros nc plus 1. So that's my coarse grid. So then the next is loop from I from 2 to nc, 2 to nc, and my solution xc, right? Oh, actually, let's call it R, because I'm actually I want to restrict the residuals, right? I don't want to restrict the solution at all. So my RC at ij should be equal to my R at what? So if it's 2, 2, it should be 3, 3, right? So I think I need to have I minus 1 times 2 plus 1, right? I minus 1 would be like the zero-based index. I mean, doing this in C or Python is a lot less confusing, I guess. J minus 1 times 2 plus 1. That's it, right? Basically, I translate the 1-based index to 0-based index, multiply by 2, and translate back to 1-based index. Okay, so this is my restriction. So, of course, we need to compute what the residual is. So my R is actually equal to B minus A times X. A is Laplacian. So my X is this. This is my R. And my RC is equal to restrict R. So here I have my RC now. It's a smaller array, right? That's what I'll be doing on the coarse grid. So now step 3. What do we do in step 3? So if we just have two grids. Solve for what equation? Solve for the error equation, right? We solve A times delta x equal to R. All right. So my dx, for example, is I want to apply the Gauss-Seidel. Starting from zeros, the size of RC, right? That's my initial guess because I don't really know what it is. And my right-hand side is going to be RC, right? So that's my, I want to, let's say, take another 10 iterations. This is my dx. So now I have my dx. I have my approximate solution of dx. Let's show what it is. I am sure of dx. It's still too big. Close all. I am sure dx. It's let's multiply by 100. Yeah, so that's kind of, I have, compared to the previous x, I have like bolder lines, right? Because I'm doing this on the coarse grid, and my convergence is slightly faster, well, 4 times faster. All right, still not very good. So I really need to this recursive methodology. Okay, so but let's just practice these 2 steps for now. And so let's say this is already my step 3. I completed my step 3, and I want the next step, step 4. What is step 4? After I have the dx. Prolongation. I want to interpolate back to the fine grid. So function prolongation. I want my dx fine, dxf, is equal to prolongate dx. So n is equal to, well, nc is equal to size of dx 1 minus 1, n is equal to nc times 2. My dxf is going to be 0s n plus 1, right? Okay, then loop again. So here, let's see. Okay, the first thing I want to do is to actually assign. So I want to. So when a grid is now a factor of 2 bigger, right? So I have this. Let's just draw something small. I have this fine grid, and I now have information on only on the only on the coarse grid. So I only have information on the coarse grid, right? So interpolation to this, if it's 1 based index, is to the odd numbered indices are just a no-brainer. I just assign the value there, right? So in MATLAB, let's actually use this indexing dxf of 1 to end, 1 to end is equal to dx, right? So this is basically the 2 is skipping for every 2 indices, okay? And then this is the red points. Then let's do these blue points. The blue points are basically what's in between these red points in the I direction. So anybody suggest the interpolation scheme for that? Just average, okay? So let's just average. So dxf, so in this case, the x direction, I'm going to be from 2 to end. Well, it should be n minus 1, right? And y direction are still the same as previous. That should be an average of dx 1 to n minus 1, dx 2 to end. Right, just a plain average. So that completes the blue points. Okay, and then everything left are the green, the leftover points, right? Filling the gap in the y direction, in the j direction. What should I do for that? Average again, right? Because I already have what's in the red and blue points. I will just do average for the leftover. So that is dxf. Now x direction is everything, and y direction is 2 to n minus 1 is equal to so dxf. I want to use what's already in dxf now. I direction is all, j direction is 1 to n minus 2. dxf is it 3? Yeah, 3 to end. Right. So this is our prolongation. Huh? Yeah. Thank you. Any other bug you found? Okay. So let's try if it works. So we have dxf should be equal to prolongate dx. Subscripts assignments doesn't match. Oh yeah, that's right. That's right. So I'm doing the x direction, so I need this. Thank you. Let's try again. That works. All right. Thank you. Okay. So I have dxf. What's next? How do I get my beta x? How do I get my beta x? Huh? I smooth the dxf, or so what is dfx? Like, how do I get a better solution of my x? Right. So I already solved this. I should add it on top of my previous x, right? So my x, I think, is already where is it? My x is, yeah, is the outcome of Gauss-Seidel. So x is the x is what I used to compute the residual, right? So I should add this dxf to whatever x I used to compute the residual for the error equation. So that is my beta x. So let's see. Maybe you can see a little bit now, right? And let's multiply by 100. You can definitely see it's gonna be a lot closer. I mean, a little bit closer to the actual equation, actual solution. And let's show this again. So x exact minus x, and that's this. Show x figure. Right. So we have the exact and the solution error. And let's zoom over here again. Now it's very much blurred, right? So that means like we can actually do this iteratively, because this is so blurred. We can even go to a coarser grid, right? So we keep doing this. So in order for us to do that, any questions on this yet? We are actually completing one multigrid cycle with a very crude coarse grid solution method, right?